very hard, and I was a bit of a laggard, sometimes catching up with the email and so on. But I'm delighted to be able to do that. And so what I prepared today is a lecture, a little bit. Some of you may have seen pieces of it, but I'm going to stress, even for the new people, two things. One is what is the Boltzmann equation, but what are the issues? Why does people sort of panics when it says it for the first time? Um, but ultimately, what I would try to make a case that this is going to be for those of you that maybe have seen it a little bit and then or have not seen it at all. I want to make the case that this is going to be somehow like when you study partial differential equations, when you start to study the heat equation, and then at the graduate level, in a sense, right? And then you need to study a problem from the functional analysis point of view, and Sobolev spaces and things that are ultimately extremely important, not only for as an analytical tool, but also as a venue to develop a very optimal computational approach or a scheme in which you can assure yourself that there will be, issues that consistency, convergence, error estimates, and things like that. And where does all that framework comes from, and how can you accomplish that for the Boltzmann equation? And I will try to see it in pieces. As Manuel said, do it very elementary. And that is perhaps the most challenging to do it in 3 hours, to be frank. So you're going to see a lot of results, but I will explain them. And I want to put them in a context that maybe becomes more familiar to you, to see, well, what you did in graduate studies of partial differential equations, and even from the numerical or analytical point of view, it would start to make sense. Okay, so as for myself, I consider myself an applied mathematician, in the sense that I do a lot of applied analysis, as I like to say it, because when you talk about analysis, it's a very broad area. I mean, you can do analysis in harmonic functions and be a very pure analyst, and with applications to quantum mechanics and so on. Well, I do it with applications to kinetic theory. And then I do numerics. And that I really became to realize that the two areas are so intertwined. And the more I understand the analysis, the more I'm empowered to even decide what is a better numerical approach, and vice versa, right? And somehow that when perhaps when you started to do the first courses in numerical analysis and the first courses in analysis itself, and aspects of scientific computing that require a lot of understanding, for instance, the stability of, what does stability mean? This is something that's going to be, I'm going to focus a lot on that question. I mean, where is the stability constant that really matters when you talk about the Boltzmann equation? And that is a theme you'll see. So, okay, so let me start by a review of the Boltzmann equation, even a very modern approach in a sense, which it was not the way Boltzmann wrote it. Boltzmann is a genius, was a genius. I mean, he's alive through all of us daily, I guess, and so he is a genius. And I want you to put it in this perspective. Before Boltzmann started to work, there was no distinction between molecules and atoms. There was no quantum mechanics, right? There was the motivation on what he tries to write is to understand thermodynamics. People was talking about gases versus fluids, and understand that there's a distinction in between both of them. And so the way he foresees this, and of course this goes into history and science, and I'm not an expert, but it's related to what happens at the last quarter of the 19th century, in which the British applied mathematicians are post-Newton and can communicate very well with the Leibniz school from the continent, as they call it, and they started to think about putting together notions or aspects of probability in order to talk about things, you know, as we would say nowadays, almost everywhere could happen, right? And so in a sense, Boltzmann generates, and it's actually quite contemporary with Maxwell, and I will bring to your attention some historical notes because it helps to comprehend what is going on. What is now accomplished, the birth of a statistical mechanics, right? In fact, Schrödinger was asked, I mean, Schrödinger is 30 years, the work of Schrödinger, 25, 30 years after Boltzmann. He was asked what were the most two significant scientists of the 19th century. That was asked in 1920 or 1930. And he singled out two. One was Darwin and the other one was Boltzmann. So I'm amazed that he skipped Maxwell, but that was a fact. I mean, yet Boltzmann and Maxwell talk a lot about it. So that's the framework of my starting point. We are going to talk about statistical mechanics, and that means we are going to be talking about the evolution of an object that you have to think it as a probability distribution density or distribution function, as we like to call them. You're not going to do continuum mechanics. We're not talking about the heat equation for temperature or the mean velocity or talking about the wave equation and looking at displacement and positions and so on. We are going to be talking about the evolution of a probability density, which is, in a sense, the evolution of a random variable, right? You may associate it. And in a sense, whatever we are going to say, the choice of the, as we like to say, of the functional space or the space, or it's a Hilbert, it's a Banach, what is it, is conditioned always to the fact of what is the outcome of the thing you want to solve, right? And so with that in mind, I'm going to be talking about elements that come from probability. The language that it's in this first slide that I will explain, it comes really from post-Katz, which did his work in the 40s and the 50s. And he really puts together the Boltzmann equation in a framework, in a very probabilistic framework. And I really like it because from that point of view, enable us to distinguish what is the Boltzmann equation in the framework of the classical elastic theory, inelastic theory, polyatomic gases, mixtures, and so on. I need to have a framework to put all of this together. And it's just the way you want to think about it that really matters. So this I took it from there is a set of not Katz lectures that were actually compiled by other people, but they are really very, very good, very interesting, and may help you to understand all of this. Maybe I didn't include my references in the lecture. I told Manuel I would send them to you the night before, but yesterday night I realized I have 108 pages, and there was more than 90 megabytes. There's no way I could send anything at that level. I can make a link a posteriori and we can do that. All right. So then we start by the following approach, and it's the connection, which is a modern view of the Boltzmann equation. And I will start by this view, and then I will get to the Boltzmann equation the way you know it, and see that it should be much more simple than you perhaps thought. So you start with an stochastic model of vector states, and see now vector states may be your velocities. In this framework, I'm thinking for a minute that is, for a while was going to be most of the lecture, except when we do some aspects of the numerics. The space homogeneous problem, and it's not that I call it, I mean, it is a space independence, but what you have to think is the following, that the behavior of what happens in a box, in a physical box, at the position X, right, is going to be the same, no matter if you are at a point in the one side of the box or another side of the box, right? I mean, imagine a problem, as we like to say, that is with periodic boundary conditions tends to homogenize, go to constant states. That happens even with the heat equation. So in a sense, what I want to focus now is in the collisional part, because that's the part that really characterizes this equation as being an evolution of a probability density, right? So how do you get there? So then you start with a stochastic model, right, of vector states. And that means they are going to be moving randomly in a set, and they're going to jump, right? And in that jump, they have MR interactions. MR may be binary, may be linear with a background, binary, tertiary, and so on, quartic. And we have the quantum Boltzmann equation now that have quartic. We have the multi-agent dynamics that use Boltzmann equation in mathematical finance that may have, 100 traders actually doing things. And so the way to understand these jumps altogether is to make some ansatz. First one, right? The intervals in between two successive jumps, even if the particles do not interact, is going to exchange, right, one position into going into positions in everywhere. So you have to trace what happened before and after, right, in these jumps. And that is going to be given according to a Poisson distribution. And that means that the jumps in times are going to be proportional to the number of particles and or inversely proportional number of particles times a constant. And that constant has to do with the rate of that Poisson distribution. That is going to set up the time derivative. It's exactly what happens when you look at the derivation of, for instance, the stochastic PDEs. The other statement, which is the what happened in between those jumps. When you have this switching of states, so the things are going to be interacting or moving around, right? And all of a sudden they start an interaction, right? And the interaction is going to be some exchange of information or something that you would know. The interaction is going to be a law. It's something that we would have to know a priori. And maybe an interaction that is elastic or is inelastic or corresponds to polyatomics, or maybe mixing, or maybe like in quantum mean field theory, is the interchange of energy states at the quantum level, given by the density coming from a condensation. So very broad framework, but it's an interchange that is going to be okay. And says that this switching of states, right, have to be quantified by what they call a switching matrices, which is, as you will see later on, is what we refer as a transition probability that takes, and a transition probability rate that one interchange has to go into the next time step, okay? So in a sense, that says if that switching matrices are time independent or time-independent matrices or operators, because any discrete system, it would actually be just, when you compute it, given by matrices that we do know, right? That actually, if that switching is time independent, then the evolution process is a Markovian one. And that is super important because that actually is speaking about sort of a time independence in the way the interchange of these laws of these states that are moving in time and hopping, and when they encounter and intersect with what certain velocities and exit with another, actually that interchange should be independent of time. Otherwise, you get into much more complex problems or problems with memory or things that you may need to address separately. Okay, now, third point, here is where the Boltzmann equation starts to arise, or the concept of the Boltzmann. If the evolution includes a birth and death rate, or a creation and annihilation, I mean, somehow that is what many people in quantum mechanics likes to talk or use that language. Then you have a continuous in time Markov process, all right, with an integrated forward equation that comes from this Poisson distribution that is pushing this jump, right? And it gives it gives an integrated master forward equation which obeys a Chapman-Kolmogorov equation for the evolution, and here it says of capital F is an endpoint, because it has end states probability distribution function that is written, right, in a strong form in this way. So let me parse this statement. It really comes from probability. I mean, just, you know, and it's very good that at one point, if you're very interested in understanding kinetic theory, you take a graduate course in probability. It's actually very, very, very important, all right? I mean, you can be coming from engineering, I mean, by the way, electrical engineers understand statistical mechanics and probability like no one. It's very, very interesting, because they actually, when they do circuits, they know they fail. And so they actually do it with a lot of probability into it. So these are components that you should have. But let me parse the equation. So what you have is, this comes from the Poisson distribution associated to these jumps, right? And you're talking about the endpoint probability distribution function. So here is a probability distribution function which may be correlated in principle, right? And so you have end states, and they may be switching. I still don't know nothing about how to do this reduction of correlations. The right-hand part, right, is exactly what you combine about this statement and this statement. Because what you have here is the Markovian switching of the states, which is the transition probability that is going to pass from one transition probability rate, because this is a rate equation, okay? Here you have the quantification of the scaling associated to the Poisson distribution for the successive jumps, which actually is going to matter a lot for how do you the scaling of the Boltzmann equation. Here, what you have is that you are actually going to have what is the state in this switching before the interaction. Look what I'm doing here. I put this prime here, right? Even if the interaction is reversible, as we will discuss later, this equation has irreversibility, okay? And that really is crucial for what we said later, okay? So here you have something that happened before the interaction, and that should be the gain, right? And then you subtract what happens after the interaction. So it's the probability after they have interacted. So that's before, after. Sort of according to a law that is given by, as we like to call, a dispersion relation associated to, or many people like to also call the resonance relation. But if you look at what is this doing, look, here you have an integration with respect to this state, with this state. These are going to be defined by a law from the previous one. We will see tons of examples, right? But what matters here is that when you integrate with respect to all the variables here and you integrate this term, what you get here is that the delta M contains the law you want to have in that switch. All right? Suppose that you want to conserve mass and momentum, or momentum and energy. That should be two Dirac deltas that would actually enforce that law at this level. And you have seen this written many times in the strong form of the Boltzmann equation. I mean, this is generic. I'm not quite talking about Boltzmann. And this actually, this integration, right? And this with a Poisson distribution, it means that it's average on all possible chance, okay, that with a transition rate from V prime to Vn according to this switching matrix, which is of operator, which is independent of time. This is what you read here. Try, maybe it's too elementary, but bear with it. So then you go back to probability, how they, I mean, if you even study the central limit theorem when you do probability, it's very, it's an undergraduate probability statement. When you prove the central limit theorem, so distinguished probability that I have a colleague, well-known distinguished mathematician, that said, probability is the most strangest thing I ever taught in my life. It is strange how you think about it, because we believe we live in a world with a lot of certainty, but sometimes it's not the case. And as you navigate life, you'll see that there's much more uncertainty than what you really think it is. But going back to the way the probability methods work, they said, okay, we are actually going to look at the way to deal in this with these stochastic equations, which in a strong form, which is something that you have here, in a weak formulation. And a weak formulation on any stochastic process, right, on which generates an stochastic differential equation is called the generator of the equation. Well, for a while, I thought it had nothing to do with what we really understand from PDEs. But in fact, it's actually a very elegant way to talk about probability in a framework that is extremely useful to do things. For instance, the central limit theorem, you are going to write an stochastic differential equation whose limit is going to go into a Gaussian or a normal distribution. And for that, use a generator given by the Fourier transform. But now the Fourier transform from this course is actually a weak formulation where your test function is a Fourier multiplier. And that actually becomes a natural generator. Much to say about that. I mean, you see a lot of interesting stuff between the Fourier transform and the Boltzmann equation. So in any case, so look at the difference in between the two objects now, all right? So written in a strong form, you get something which, as I said, the positive term, so these are probability distributions, F is positive, so you have the switching matrix, which assume to be positive, it's a transition probability density, so that should be positive. And then when you actually get into the weak formulation, what you have is you multiply by a test function. You assume that your test function has to be sound for the problem you're dealing with, and that will depend, in fact, a lot on what is the transition probability density. But the important thing is that what it does, it swings the interchange of velocities that appears in the probability density in the pre and then minus the post into that in the test function comes in the post minus the pre. And here is encoded the entropy bounds and entropy theory. And you will see how it works, okay? So it's very important. If you do elastic theory, it doesn't matter. Sometimes it says, well, the pre, the post, you go to the books of Cercignani, the books up to the 70s, they always put the prime on the right and they talk pre, post, post, pre, and you have to sort of follow it up. And I hated that. So I started to put my prime so I can remember it. And I learned that because in inelastic theory, you must do that because the interaction is not going to be reversible. Reversible, right? Elastic theory has an irreversible interaction. But yet, this statement has to do with the fact that it's going to come next, okay? But This is fine, and this is a weak formulation. This came up the same, this came up the same. All I did here is I was able to put the probability density, the endpoint, multiply by the difference of the test function now in the pre minus, in the post minus the pre. All right, and you always talk, this is, you see, let me clarify, V is the one that is fixed here, it's my reference velocity. So I talk about pre with respect to V or post with respect to V, okay? All right, so now comes a crucial step that actually Boltzmann envisioned. And Boltzmann starts with an endpoint probability density. I mean, he phrased it in a much more physics framework, but this is a fundamental assumption. Suppose that these are evolutions that corresponds to IID continuum random variables, and that is indistinguishable, independent, distributed continuous random variables. All right? That means all of my, so if I'm thinking of molecules, okay, I'm going to give them a shape. All of them have to have the same shape. Let's think of circles, okay, or spheres, right? They have to have the same properties. They have to have all the same mass, all the same objects. And so I'm going to be deriving first a scalar equation. They have to have, so you have to have a set of particles that are identical. And it doesn't matter when you look at them as where the random positions may be, they have to be indistinguishable. So you can do this switch and that would be fine. That allows you to state, and so this, that actually properties also, it have to be probability measures associated to probability density measures, which has the exchangeability property, okay? And so you can reduce that system, and not to talk about the endpoint probability distribution function. And so you are going to use what is called the propagation of chaos, that in German has a word that I can hardly pronounce, and I'm sure it's all very familiar to you, which is the just say it, Manuel.
I have to say it. Stoßzahlansatz.
Yeah, that's right. That is the word. Okay. I cannot. I have to take a class of German just to learn that word. Okay, and so it says the following. Suppose that you start with a system that initially the probability, the endpoint probability distribution function is decorrelated. That basically means, right, that if I start with an, and of course it averages to 1. That is very important because you can always renormalize. I mean, we will talk whether you renormalize or not. It's a mathematical tool, but for the derivation, you want to do it this way. And that means that the endpoint probability distribution function is the product of a single point probability distribution function. And you label the velocity particle bk, and then you multiply in all of them case, right? I'm sorry, here I should have put this capital. Okay, sorry, no, I'm saying it's not the capital. I keep that because here is an n tupla, and here is a single v. So vk maybe it's in R3. That's why, and I didn't stress, this integration occurs in the you know, is the weak form. Look, this integration is in the dimension of the space times the number of particles. So you can do this in R3, in R2, in Rn. You start with n probability, the n states. And m is the number of conservation laws that you may have, or laws. So if you have 1, you put whatever that condition is. If 1 is conservation of mass, if not, it goes on. All right, then you go, propagation of chaos says if this occurs initially, then you have to have a model that actually allows for this to hold for every time. So the propagation, so this concept of chaos, which is the indistinguishable position that allows you to analyze an object, a probability distribution as a product of single point probability distributions, that needs to remain for all times. Okay. And once you have that, and that is an answer, and people is still struggling to prove this seriously for the Boltzmann equation we use to compute aerospace dynamics, okay? But, you know, it works for some cases, but it's not so clear how it works better for others. And so it's an ongoing area on ergodic theory in mathematics. So then that allows me to go into what we call the weak formulation of this object becomes a process. So a process that can be reduced the hierarchy by just integrating this equation with respect to different variables. And that would take, people would call the marginal. And that is called the hierarchy reduction of the Boltzmann equation. I'm not going to talk about that. That's a little bit cumbersome. But let me set this. If that process was reduced, say, to an important configuration on which a binary interaction matters, and is actually classified by, said, in elastic theory, as we like to say, the conservation of mass and the conservation of center of mass, and the conservation of relative velocity, or the conservation of local momentum and local energy, they are equivalent. Then I may write the variables this way, and I should say that this law, this is just the relative positioning between the two, right? But the law, okay, that here comes here. This is identical to write that V plus V star is equals to V prime plus V prime star. I could put the primes on each side because this is reversible, and that V square plus V star square is equal to the same thing after you prime them. Maybe you have seen this before. But the reason why I chose to write it for you this way is because all the analysis, even in Fourier, it comes from this representation, which is the center of mass and relative velocity representation of the Boltzmann equation. Even how we derive the Landau equation comes from this view of the variables, okay? All right, so that basically means that if I just write the reduced equation, so now I'm going to assume, right, that I have a single point probability distribution function here in that hierarchy reduction, and that would be another lecture, and I'm not going to do it today. You can replace this object, right, as the integral of the product, but when you look at the switching part of the matrices, this part, that becomes exactly that. The capital F now is going to do a hierarchy reduction on which you have the single point is going to at one point be a correlation in between one point, so a position V1 and a position V2, or a position V and a position V star. And that is where you say you factorize. And that factorization means that in the framework that you get from the factorization, occurs in V, and here would be V star. But V star minus, but V minus V star is U, which is the relative position. So I could have put here V star, and this is a G kernel that actually gives, make the two things combine. So what is that kernel? That kernel actually is super important also, and it becomes, and it's like what it comes in the weak formulation. It obtains all the information that you saw in this equation, because it has the switching of metrics, it has the law, and F becomes now localized, and that capital F in this case is the correlation of these two Fs, but in V and in V star. Okay, so this looks difficult. This is the easiest part to do. Go to the book of Tertulliani, and I could do, and it's just exchange of kernels. I say you do an exchange of coordinates. You integrate the exchange of coordinates. So you do pre to post, and then primes to unprimes, and this and that, and then you gather and you get a formula of this kind. It's exactly of this kind. But now I want you to focus on the structure, and the structure says what you have here is. So the right-hand side is the evolution of the weak form of F, the left-hand side. The right-hand side, right, is now something very unique that basically says, looks like a convolutional form here, but it's multiplied by a weight and it's integrated twice. So it's not a convolution. But what we like to call this is a double mixing weighted convolution. Because I'm actually mixing the particles, and that mixing of the particles comes from what happened with this weight. And as you will see later on, the weights are highly oscillatory. And that is actually what characterizes the Boltzmann equation. Written in weak form, it's very transparent. You'll see it in a minute. And we said some other thing. When phi are polynomials, we obtain equations for moments of evolution dynamics. So in other words, that is becoming, is that this mixing, right, have what you like to call what happened and moments in probability, in statistical observables. And actually, I like that word a lot because what we are going to be basically following is what we observe of this equation. You write the heat equation and you look at the decay of energy or temperature or whatever. You look at the wave equation and you see what is the position and the velocity on the string as you play your guitar. But when you do this, what you are doing is a much more complex object. You're looking at the evolution of a probability density, and this object actually has been mixed completely. And the things that you naturally observe are averages after you multiply by some polynomials. Well, statistically or probabilistically, this is to take the expectation of order, the expectation, the variance, and the kurtosis, or whatever names you want to give to nothing else that take your evolution with respect to an average polynomial. So what happens with that polynomial, that average goes into this master Chapman-Kolmogorov equation written in weak form can be actually classified into this weight. And that is great because even this is what we do when we compute the Boltzmann equation, be by a spectral method or be by a finite element. All right, and I'll go back to that. I mean, at one point I'm going to speed up a little bit. I'm just trying to get you in the right state of mind. So, okay. So then let me just say a word about this weight. Maybe this weight functions may be nonlinear. That's not a problem about the things. They encode all the information about the dynamics of interaction. So molecular chaos sets the time in reversibility. So this is important. Now this is in the post and this is in the pre. When I write for you the entropy theorem, the H theorem, you'll see that how all of this can vary alike. Because if I switch the sign, I switch the sign of the entropy, and then I would get something that may not be what we want, which is the bounds that we get from the entropy. Second point is the interaction law may or may not be reversible, determines the steady states, and we call phi collision invariance if it actually makes this way to vanish. And that is actually, it's a framework to talk about things. And then the collision frequency encodes the properties of the solution, like Dieter valence and decay rate to equilibrium. So there is a big difference between hard spheres, which are the particles that are going to be bumping, and the particles that comes in plasmas, where electrons we know that have repulsive forces, so the particles may be getting close and then they deflect and go out, right? That is going to be encoded in the transition probability, which is a Markovian process, which means it's time independent. If it depends on time, then we have a different way. I mean, we cannot do that. So let me then focus in the elastic theory. And I have these diagrams, and I don't expect you to digest that, but what I did this diagram is important in the following sense, that I want to have the representation of the velocities. So I start here, right? And I have, so you have a first, a V star and a V. You trace first your relative velocity, which is the diagonal. You actually look then at the circle with this diameter, right? And the distance of the magnitude. So the diameter is the magnitude of U. Trace that circle, choose an arbitrary angle, and you can call it the scattering, or you can call it the impact angle. This is the impact, this is the scattering. It's all described here. I'm going to give you the lecture so you can read it carefully. Why that doesn't matter? It matters because the way Boltzmann writes the transition probability, it actually is fundamental in as a function of, he says, of the eta. I'll talk that later on. But the description of how the integration is going to come much more handy for many things is in terms of the scattering. I'll give you some other diagrams later on, but essentially is the following. Maybe I can do here a little picture, and is that you have a particle here and you have another particle here. They have to be, so they are moving, they are identical. Take this one at rest. So this is moving with a velocity. Sorry, it didn't come very much nice. All right. And so they are going to touch. And what the time they touch is when this particle is about here, right? So they have to be, first of all, the difference between these two here is the impact parameter, right? That matters a lot in the derivation of the Landau equation. But what happened is the eta direction is this direction. It's the renormalized vector in this direction. That is the impact direction. And the scattering direction is the one that at the time of the impact, you have this vector is going to be sitting here. So let me change colors. So this vector is going to be sitting here, and it's going to reflect elastically in this direction. So this is the, so this is U before and U after, okay? And then you're going to have that, then if I take this direction here, all right, this is the, so let me put it the other way around because I'm going to usually use it later. So I'm going to put this is the after. And so here what I have is the parameter theta, that's the scattering angle. And so U prime hat is the scattering direction. Okay, and you will have to make a choice on how you write the equation. But I tell you this, and you keep on doing it, Manuel, this is for sure. You go to the literature of 20, 30 years ago. They started people in the French school to look into the different aspects of Boltzmann equation. There is a lot of confusion when they change variables from scattering, from impact direction to scattering. And that is crucial because you made a mistake there. It may be a Jacobian of a transformation. You change the decay rate to equilibrium. So your numerics is extremely sensitive to that. Okay, so you have to be very careful. So, you know, another interesting thing is that you can actually, and that is going to be very important, again, for the Landau equation, you have this part of the triangle, which basically says that the sine of theta over 2, right, is here, I have it written, multiply by, and this is a vector, and this is a vector, so directional vectors, and this is the correct way of looking at it, is that this direction, all right, you can obtain it by this direction times the sine of theta over 2. You know, all of these things, what do we need them? So, well, wait, you see, okay? But it really matters. Okay. We also said that when the angle theta is 0, that means that the collisions are going to be grazing, and when they are pi, that means they are head-on. So that the head-on is that you go directly into something and bounce back, and grazing in case you seems to be impinging, but you really don't, and they are very, very small. Okay, example 1, the linear Boltzmann equation. All right, the linear Boltzmann equation, if I write in a strong form, you see it this way. Here is with a background, we call it the scattering. So the weight function here is going to be the transition probability, the Markovian process is S. F now is a single point distribution function. And I did something here that I didn't preach about it. I put the primes on the right, and this says, well, you know, in fact, I have a background with the probability density. So because I have only one variable, I just didn't care where I put the prime. So maybe I should put a tilde because it's an integrating variable. Now, if you take, if you assume that this matrix is symmetric, and I bring in this example because that's what we use, for instance, to study the Boltzmann equation, to do the simulation of charge transport particles in a small lattice, in a semiconductor. And what you're looking at is the collisions against the background. In that case, what you get is that the weak formulation becomes in this form. Look, here's the Markovian matrix, here is F, here is the weight function. And I could actually think that my weight, right, and I didn't specify the integration here. Okay, sorry, I forgot here, I'm missing a decay. That's important, because I have to have a double integration with respect to that. And that could be in RD. So the switching law here is not the same. It's just a linear process against the background. There are no collision law, okay? That actually makes it a very unique, very easy problem in some aspects, not another. First of all, is that has only one conservation law. The linear Boltzmann equation has only one conservation law. But on the other hand, it has infinitely many entropies, because you multiply by any function. So take a function that is in the kernel of this operator. Take a function that nullifies this kernel or this kernel, right? The Maxwellian distribution would do it. Sorry, a Poisson distribution in V would do it, in K would do it. Then you take actually the average now. Instead of a polynomial, you take any monotone function of the solution, renormalize but the element in the kernel, and that gives you an inequality, which is a signature of stability. So this is a very robust equation, has only one conservation, so infinitely many entropies. That means, okay, you have F log F, L2, and so on. So these equations are wonderful, and they are very easy to manipulate, for instance, in Sobolev spaces, okay? The typical example in which we use them, this is the Boltzmann equation for hot electron transport and on AK energy bands, and according to exchange of probability that comes from the Fermi golden rule, scattering with absorption and emission phonon rates. And it looks like, wow, what is that? Written in weak form, it's just a bunch of things, as you can see it here. They put it in here, right? And that's why we actually compute this with the discontinuous Galerkin method. All right, it's very simple and it's very reliable. Okay, one conservation law. All right, example 2, the Boltzmann equation. You saw it before, now I'm going to write it. You saw it only in weak form, 2 slides or 3 slides before. Here is collision diagram. Now here is the weight. And then you realize, oh, I hope you don't see this, I'm not sure. Oh, what did I do? Sorry, I wanted to eliminate that. Okay, I did. All right, so the whole point is that this transition probability, we make usually assumptions of what the kernel is, and that is the Markovian switching state. And here we actually classify them with respect to this power. And that power, we call it, if you have to be 1, is hard spheres. If you have it positive, it's going to be hard potentials. Polyatomic gases actually goes all the way up to 2, right? And that actually many of these calculations come for free or even more. If you do Maxwell molecules, is 0. Why is that important? Because it has explicit solutions, and it allow us to do a lot of learning, and you have a closed equation in Fourier space. If you go negative, you go into soft potentials. That is more useful for chemistry. And when you get to the Coulomb interaction potential, you are doomed. There's no Boltzmann equation any longer. You have to do Gracie collision limits, and Landau wrote it. And that I explain it in a minute. So, but look, this is the Boltzmann equation in weak form. Think if you have to compute something. I mean, just pre-compute the weight. You have here a switching, this bilinear form. You can write it like a matrix, in a basis function, a transport on this side, and you integrate that object with respect to the weight. Look at the strong form of the Boltzmann equation. What would you do if you look at that equation first with the transition? I mean, it took a lot of time, I believe, to understand this, that the least you want to do is to use it in strong form. There's one important use of the strong form, and you need it for doing L infinite estimate, which I really like, and we used it. And it's very important to understand boundedness of a solution. But except from that, I don't find any really use that actually can give me any asset in order to be able to do something much more important. But regularity theory. The Landau equation, that's example 3, okay? The Landau equation actually was calculated by Landau on the following ansatz, and I'm actually taking some features of some work that was done by Degon and Lukin in 1990. Basically what you do, here is the diagram of the elastic collision. Here is this a triangle that I told you. You look at what happened between the difference of pre and post of the velocities, and look at this and say that the relative velocity times the sine of theta over 2 is the difference of the pre minus the post. Then the post minus the pre. Then what you have is the following, and Landau used it without quoting something that was done by Rutherford. It says Rutherford in 1911 said, if you are going to look at potential electron-electron interactions, the transition probability from one state to another is given by a function that is going to be to some very singular function that has to be a function of the half angle here, because that's exactly what you're looking. That's what he calculates, the deflection, what happens with the velocity from one to the other with respect to the scattering. And he says in 3 dimensions, you have to have this eta to be 4, right? And but if you don't, you can actually play with the dimension. Physicists do a lot of stuff nowadays in 9 dimensions with the string theory, and they started to look at these collision operators. So, all of these things may be generalized. And then he calculated, Landau, an object that if you write it in a weak form, a posteriori, it gives you a weight function with this structure. So that allows us, for instance, to do several things. So this is the weak form of Landau. This is the strong form of Landau. That's what Landau wrote by actually assuming that F was differentiable, took the strong form of the Boltzmann equation and started to do the Taylor expansion before or after at this level. And that is a mess. If you do it weakly, it's great, because you do the expansion on the test function, and then you do exactly like you would do, for PDEs or asymptotic dynamics. Then you go back, write the strong form, and the strong form gives you an equation that has the structure in divergence form. It's a Fokker-Planck that comes from the Gracie collision limit, and that actually gives you a form that is non-local and quasi-linear equation, in the sense that, look, here you have an integration. So this is the strong form. So you have a divergence, and then it has a diffusion. The diffusion term actually depends on the transition probability obtained from the Gracie collision, and that's the Landau kernel, right? Multiplied by F and V star, which is exactly what it would give you as you do the calculation back. So this integral right, is something that depends on V. You are integrating in U. You put it here. It's a non-local diffusion and quasi-linear. Okay, so but we actually compute it with as you will see, with the spectral methods, and we are now starting to do it with Galerkin as well. So then this other term is an advection term. I forgot to put the V here, so there should be a V here. I have a blue. You should have a V, and that E of V is actually this object here. Look, it's almost the same, except that here I replace F by the gradient of F. That's what you get here. All right. So it's very interesting that you get to obtain these equations, and then immediately, because you can only view it and see it from the Landau equation, you can inherit many properties like conservation and entropy and so on. Conservation laws. Conservation laws then are going to be the following. First of all, as we said, if you test by these polynomials, I get the collision invariance. Why is that? Well, because if you have this conservation law, think of the following, right? What I have here, the f of v or v star or v minus u, this is g, the weight, right? So here you have to put the phi before, no, after the interaction minus before. But I have, so when you put 1, it's a clear 0. When you put v, you have this conservation law. That gives you another 0. When you put v squared, you have this conservation law. That gives you another 0. And this gives rise to the dimension plus 2 collision invariance, which implies dimension plus 2 or 5 in 3 dimensions conservation laws. The H theorem. The H theorem also comes from the weak form. Why? Because now I did exactly this. If I put G, okay, so take phi, put here, okay, let me set phi of V to be the log of f of B. Use the weak form. When you use the weak form, you have here f star, f, so f on V star, so this is f on V star, which is f on V minus u. This is f of B. And here you have this weight. But if you look at the logarithmic function and you write the f, the f of f on V prime plus the log of f of V prime star minus the log of f, and do the algebra of the logarithms, then you get this expression. And this expression has a sign. And it's very important that this sign came because you put that in the weak form, the primes and after and prime are before. Okay, so it's really very interesting how you are going to be looking at that. If you if I would have write the weight in the opposite direction, right? So if I would put here, if I would have put a minus with this primes in pre and plus here, I get a round entropy, and I would not get a bound for the entropy. All right. I just mentioned also that the entropy has a very way. Some people actually like to call the entropy minus the entropy, but if you call it minus the entropy, then it's fine because you have switched the whole process. Is that you switch the sign of the equation, so it's not that you change the pre and the post. And then you have the Boltzmann theorem, which is something that Boltzmann proved as much as Maxwell did, and it's the following: that if you have in any state for which whose logarithm equated to m is 0, that is equivalent to say that the logarithm of that state has to take this form. Because why is this minus here for C positive? Because you have to have a probability density, and that means it has to be an integrable function. And that forces that minus sign. Otherwise, a probability that doesn't integrate to 1 would not be good. And so, and then you have much more work and estimates that you look at the relative entropy, and that you get that this quantity also has a sign. Okay, and then you can get the Tangram inequality. And this is a very old slide because I wrote this going faster than any polynomial. This is the statement that actually allowed Villani, it was quoted in the work with Toscani on his Fields method. By now we do know it decays for hard spheres exponential. Okay, so it's a very interesting thing and a lot of references here. So the overview on kinetic to hydrodynamics, I'm going to very quickly, I guess most of the students may know it here, and the connection. Should I review it, Manuel? I don't hear you.
Yes, I'm muted. So here we go. I don't think that many students know this, but in time, you should make a wise decision. How do you want to spend your time on the other 90 slides?
Okay, well, may not use them all. Okay, so, all right. So roughly speaking, there is a connection between classical fluid dynamics and Boltzmann, and comes through looking at the Boltzmann equation with the space now, which is the material derivative on a Hamiltonian dynamics that says the position, the rate of change of the position is actually going to be the velocity for my particles, and that actually gives you the sorry, I'm gonna take this out. It's going to give you the form of the advection operator, and then you equate it to the collision operator. And you know the collision operator has the collision invariant, right? And so in particular, what you have is you define the moments of the observables that we said, and they have all names that this is mass, momentum, this is the associated to the variance. This is going to be the stress tensor associated to dynamics, and here is the heat flow or the heat flux kind of or moment associated to the heat flux. And these are names that you give to the variables. Somehow there's nicknames that start to take this form or loss. I don't have time to go into these details, right? But for instance, this is the current, and then that means that the current is the density times the macroscopic velocity. Here you got so if you write it in terms of the, this is going to be associated to the total energy, and the total energy, you write it as the density times the square of the speed times the dimension of the space, and the density times temperature, or you can actually enter this in terms of internal energy and so on. So it's a lot of ways to write the equation, to write the macroscopic variable. But the whole point is the following. If you look at what is in the kernel, remember the Boltzmann theorem, the kernel of collision operator is a Gaussian distribution, and you assume the Gaussian distribution depends on 3 parameters. I mean, a Gaussian distribution is characterized by 3 parameters: by its mass, by its mean, and by the variance. You can, it has that property. And then you choose them to be density, said, mean velocity, and internal energy, which actually has to do with the variance of the collision operator. That's why it's a quantity that appears here. Then what you have is the following. You call these quantities. This is going to be the stress tensor. It happens to be that when I evaluate it on a Gaussian, if you take it, if you take the values away from the diagonal, this is an even function. This would be an odd. It gives you 0 on the diagonal. That gives you this expression. And same thing with this vector qi. You get that this quantity, this is an even function, this is an even function, this is an odd, that comes up to 0 whenever you evaluate it on a Gaussian. And then you have a relation that connects actually the internal energy to temperature. Then I can write the compressible Euler equations for density, mean velocity or macroscopic velocity, and temperature. And it's exact. So the Euler's equation means that the statistical flow is always a Gaussian in the velocity space. And that is a delusional thing. A shock would not have this property. A boundary layer does not have that property. So it's an interesting connection, but I don't find it that useful, all right? What is more useful is what happens if you deviate a little bit, right? By assuming that you're going to have a stiff parameter here and be very close to the very close to the kernel of the collision operator, which is this Gaussian. That basically means that your solution, in principle, you're going to do an asymptotic, and that is going to be that Gaussian state, that's the F0, plus a perturbation of order epsilon, right? And then what happens is actually very interesting, that you calculate what were these two quantities that happen to be zero on the Gaussian. That you get some deviation there, and you need to account for. And this is going to be, so the stress tensor now has the stress parameter and the viscosity parameter, and the quantity Q, which is what we call the heat flow vector, right? It's not zero, but you have a contribution of those that are of order of epsilon. It's a big O here in the other one. And that gives, if you do the Chapman-Enko expansion, or you took a sound moment closure, you obtain the compressible Navier-Stokes equation. All right? Well, because there are expansions, there are errors, and Manuel Torreon is an expert on how to handle those things. All right? How do you overcome these errors in expansions and so on? So I let Manuel to elaborate. You should do the summer school. The Fokker-Planck-Landau equation, I actually describe it a little bit, but I want to stress that this is actually going to be done by looking at an expansion now, not in epsilon, but in the grazing collision limit, in the fact that this angle is going to zero, or these two distances are going to zero, or these two positions are going to zero. And in that case, you can actually calculate very much what is this kernel that shows up here in a strong form. And that is what I wrote in the previous slide. This is kind of repetitive, so I don't need it. The equation that you saw in the weak form. Sorry, this is written in a weak form, and this is written in a strong form. And I put that twice. Another example, the linearized Boltzmann equation. Why do we care about the linearized Boltzmann equation? We do care because we want to actually, we can study the spectral gap. We can do the calculation of the Rayleigh quotient and see how is the decay rate of equilibrium if you know very well what is your weight F and the weight B, sorry. And the weight B, as I told you, that actually classifies the decay rate to equilibrium. In the same way, the Rayleigh quotient is used to obtain the decay rate to equilibrium for the heat equation if you have an object that has a coefficient inside the divergence form that is not constant. So from that, we use a weak form, you use this Dirichlet form, which gives you an entropy because it has a sign. You can see it here. And from there, we calculate the Rayleigh quotient. And I don't have time to show, but we have an incoming manuscript on where we computed the really spectral gap. And you can see that if the potential is very soft, like Landau, you don't have a spectral gap. You have a degenerate gap. And then we learn how the Landau equation decays. And we use it to be able to talk about the validity or the verification of our computational approach. Decay rate to equilibrium, then it goes into the fact that we want to see what happens as you go into the infinite states. And this is very rich. And then there's one thing I wanted to point out here. The decay rate to equilibrium, if you look, is measured in L1, in L1, in L infinite, right? If you do it for the space homogeneous, and that was actually a work that is kind of old-fashioned passé. Now we have a lot of interesting things, but it's done in a Banach space, not in a Hilbert space. But if you do it for the linearized equation enables you to work out in Hilbert spaces. Because you have L2 norms, you can actually have objects that are going to be very sound in L2 spaces. And then my next theme, after I just do that and I do a break, is the following. if I want to do a computation, I really am going to be discretizing. I'm going to be using matrices. Matrices always live in Hilbert spaces. You can always, they are discrete objects. They may be very large. They are discrete objects. The problem is you're approximating an object that is in an infinite dimensional space. Yeah, question. Can I say that I have estimates of the Boltzmann equation in Hilbert spaces, right? Can I talk about error estimates on which I have even Sobolev norms, right? I mean, I want to say the Hilbert space by Sobolev space. Can I say that I have, 3 derivatives, 4 derivatives that are in L2, right? If I can do that, then I know how to do error estimates. We do know how to do error estimates, and we tap them to the analysis. So we want to get to the point that we can analyze that. And in order to analyze that, we really need to start by the Banach space, which is L1 with moments. You cannot escape that. And that is actually perhaps what I'm going to focus in the next hour. Last, so you know, the Fourier transform. What happens if you look at the weak form of the Fourier transform? Well, you can do this calculation. We did this with Harsha Tushka-Bujaman in his thesis paper. I have all of this is posted online, and we use it along with Shevhak to compute the Graysing collision limit and many other things. And essentially, the Fourier transform of the collision operator, I start in the first step, gives me a weight on F. This actually had been used by Devillet to do some estimate. So it's the Fourier transform of F times its translation by U, okay? But you can keep on working on it. This is what we did with Harsha, right? The weight took this form, okay? And you see here the full multiplier is the test function on the pre and the post, and I took a piece that was here in my KV, and I use it to generate this Fourier transform. That's what Devillet did. But 2 things about this take. This is the probability density. I'm assuming I can split it, and the probability, the collision kernel, the transition probability rate, and I can split it in a potential rate due to the gamma and a function of the scattering. And then that is multiplied by this expression, which is a Bessel function, which is nothing else than this, right? That's actually very handy. Why? Because I can obtain further on this expression and take the Fourier transform from U to psi, right? And that would actually give me a perfect convolution in Fourier space with a weight. So this is not going to be n log n. For the Landau equation is, because it's magic, that the weight in the Landau equation splits in Fourier space. You can actually show it if you write it in spherical coordinates. But if you keep it, right, in Cartesian coordinates, what you would have always in general for the Boltzmann equation, a weighted convolution in Fourier space. Yet, because you have formulas like this one, we compute this and we pre-compute it. And then we can use a fast Fourier transform to do the calculation. And it gives amazing results. And I will show you that later on. So this is interesting because you can actually view the G hat, right, as the symbol of a multilinear integral operator in the same sense we use to look at the symbol of the Laplace equation or the Laplace equation for the Maxwell's equations. The symbol is what is called the Hankel function, right? Hankel functions. The symbol for the wave equation, which allows you to do very easy solutions using the Fourier transform. So the Boltzmann symbol is much more complicated, but it's very handy computationally. And it's somehow related, you may view it as a dispersion relation associated to this flow. So then I think it's a good time to stop, and I will talk a little bit about the theoretical aspects. I will stress on the stability property, and then we go into some simulations if we have time. 5 minutes is okay, or is too much? or it's too little?
We can do 5 minutes. Maybe there also a question.
Any question? Yes.
And if we are ready to go, we will continue. Andrea, you had a question, but I think that this was kind of, we chatted also.
Yes, but just to clarify, your sigma is the post-collisional velocity difference between v and v star, right? Because at some point you used when you explained the
that's
vectors,
a very good question. Yeah, sigma here, which I use it well at the beginning. So sigma is this expression, right? So sigma is in the direction of, so sigma is u prime over u. But in elastic theory, this is u prime over u prime, and this is u prime hat. And then what you have is that u dot sigma, u hat dot sigma is the cosine of the scattering angle. That really matters.
Ah, yes, also. Thank you very much.
Good question. Yeah. Yeah. So, and that is important. And as you put it all, it's like this puzzle. That's what I said. You cannot, I said once, you have to get the collision law under your skin. You really need to think particles. You really need to think what is going on here. And it's not, maybe you don't acquire on one lecture, but you need to put it together in a good framework to put it, to understand.
Also, what do you mean by symbol?
Oh, okay. The symbol, when you look at the PDEs, for instance, the Laplace equation, right? Or the heat equation, they say, well, I can actually solve the heat equation in all space by taking the Fourier transform, right? And the Fourier transform, what it does for a partial differential equation, this is not a partial, this is an integral equation for the collision operator, but for a partial differential equation, this transform exchange, right, the derivatives by a polynomial term in the Fourier variable. So you look at the Fourier transform of the Laplace equation, right? And then you get, you're going to have
You got muted.
My mistake. I misclicked. Irene.
What is happening?
I think I muted her accidentally. And that's my mistake.
There it is. All right.
I don't know.
Talking too much. So what I'm saying is you differentiate. So you look at the Laplace equation and you take the Fourier transform. And so you have to do 2 integration by parts. And that is going to give you some k squared, the absolute value of k squared, right? Multiplied by the Fourier transform of f. And so you end up having a time-dependent equation with an algebraic k number, okay? Multiplying the equation. And that is the symbol. Okay?
Okay.
I mean, for PDEs, I mean, there was, when I was a graduate student, that was a big thing. I mean, what to do with symbols. I mean, can any symbol generate PDE? And there's a lot, it's an army of people talking harmonic analysis. And I've been asking whether this would be a good symbol to some good numerical harmonic analysts. They have never studied this subject.
It's a fancy word, but I think it's related to dispersion relation in the
yes, right. It's the dispersion relation. It's exactly that. It's exactly that.
Yeah, you know, dispersion relation when we studied wave, it's essentially wave.
It's essentially the waveform, right? That's right. It's the dispersion relation.
Yes. Okay, no, I just wasn't familiar with the term symbol.
You can, some people said the resonance condition, right? That's because if you put a Dirac delta inside an equation, or the dispersion relation, or the symbol. They are all related in you know, different frameworks. Versus, you know, the difference between an operator and an equation. What is the difference? Well, the operator is just the object without equals to something.
Cool.
So the Boltzmann equation equates something. Okay, equation means to equate. Okay. Right. Okay, 5 minutes in.
Maybe another question. I mean, now
yes.
it's time, so it's hard to interrupt you while you're talking. So maybe this is the chance, right, for anybody to ask a question. So we are all ears. But maybe we're just looking forward to the numerical simulations.
All right. Okay. I will say a few words about that, and then I will move on why we care about the simulations.
I'm looking forward. Okay. So maybe you just.
Right. Okay. That's what I thought. You know, I didn't know exactly what the focus is, but I will do that. Okay. All right. Okay. I'll be back in 5 minutes then.
Okay.
I just warm up my coffee. Let me see if I can get myself California now.
You have another class today, I understood?
I have, yeah, I'm actually in California because my son had some surgery on there. And so I wanted, and it was a spring break last week, and so I stayed another week.
So nicely for you in the morning of Texas, but now you're...
Yeah, right. No, it was going to be perfect, right? It was 9, and so, but yeah, I teach at 2 p.m. Texas time, but it's okay. It's about...
Yeah, but it's going to be...
So it's 4 hours from now, 5 hours from now. So I'm fine. I can recover.
Yeah. So you tell us what you want to tell. I'm looking very forward to the second part.
Yeah. Okay. So let me see. Oh, Milana Pavek is there.
Milana is there. Probably.
Yeah, right. Look at that.
She's okay. She just entered. She probably didn't hear you, but it's perfect just for the second part.
Right. That's right. I haven't said anything that is important yet
for her
with respect to the work we did with Milana. Yeah. So Milana, are you there?
Yes, I'm here.
Hello. How are you? Are you in Germany or you're in Serbia?
Still in Serbia, I guess.
Oh, okay, okay.
Yes, I'm still in Serbia.
I'll contact you later today, okay?
Yes.
Right. Okay. So, all right. So some of the basics aspects and here. So this first slide, you already all heard all the details and what is just a very fast review. The Boltzmann equation, if we write it in weak form, you get this double-weighted mixing convolutional structure. The transition probability rates, its Markovian switching state operators is usually characterized in this form. The collision invariance and the H theorem, and that actually enable us to view things in a how do you solve the Boltzmann equation. And this actually is interesting because it would allow us to do this very generic framework that we were able to, it was suggested by Bressan, but he had somehow a mistake in checking this condition in this unpublished work. I believe he probably realized and never published it. It was part of the CISA school, but we reworked it with my former student, Ricardo Alonso, and we use it in many, many frameworks. And most lately, this is an old slide, we use it with Milana for the case of mixtures as much as for the polyatomic gases. So, and I bring it to your attention because I'm sure most of you have ever heard about the Lax-Milgram theorem to start solving problems, right? I mean, you cannot do anything without it. And the Sobolev embedding and the Sobolev constant and the Poincaré constant, and that has to do with the stability, with the decay rate, and so on. In the last 3-4 years, I started to think, after we saw this statement, which was proposed by Bressan, you can solve the Boltzmann equation using a classical ODE theorem in Banach spaces. And I mentioned that in the first part. The starting point is not going to be solving a Sobolev space. So the Sobolev embedding doesn't work, right? what it works is start to do the natural, you solve things in the natural space where the equation gives you some information. And that is L1 with moment, integrability of moment, observable. That's why it's the highlight here, right? So what the result says replaces, in a sense, the condition of Lax-Milgram by this statement, which essentially says that if you have an operator, any operator, right? And then you take a Banach space, an operator well-defined in the Banach space, okay? And you take a subset of the Banach space, which is bounded, right? So if the element is bounded, then that means well, okay, let me just say that it's bounded as a set. I think it's always controlled by a constant, any element on the space in the right norm. Convex and close in within the Banach space. So omega has to be a bounded convex closed subset in the Banach space. And Q is an operator satisfying three properties. Helder continuity. Helder is not Lipschitz. If I can replace this by Lipschitz, which we can do for Maxwell molecules, then this condition would be, Lipschitz condition would be essentially enough for existence and uniqueness. But the Boltzmann equation does not enjoy that. Hard potentials do not enjoy that, even much less soft potential. So the conditions, and we know how to do this for hard potentials, are you replace Lipschitz would be to have this, sorry, here is beta, beta of 1 needs to be replaced by beta between 0 and 1. For hard spheres would be about 1/2. For any gamma, it would be gamma 2, okay? And then you need something else for existence, and it's called the subtangent condition. And this condition is very technical. You have to prove it. I will not go through the details of today of this, but we had it in very much detail in our work that I'm doing with Ricardo, not as much as we have it with Milana, in the sense that this is the condition that would actually generate an invariant region as you move along the flow that is coming from a Poisson distribution, somehow that time-dependent part. Okay, so this is really an existent theorem for the space homogeneous setting. Okay, because if you have to do so I cannot do this statement for the whole advection operator of the Boltzmann equation. If I would be able to do that with this, we probably would be very, very well known, because that means we could do the work, we could improve infinitely, you know, in a very high grade, the work of Lyons and Diperna, for which Lyons was awarded the first medal. So this is one of the shortcomings of the Boltzmann equation. The still existence in the space dependent, an X-dependent case is much more cumbersome. But that would be enough to have existence within the space homogeneous. And then there's one other condition, which is it's one-sided Lipschitz condition, which is a sort of what the minimum that you need to obtain uniqueness. And then this theorem, which is rather abstract, so you check 1, 2, and 3, then you know that there exists a solution of your problem for an initial data in the bounded subset that you have to choose, you have to find, right? And is unique in the set of continuous functions if you look them in, so continuous in time, sorry, if you look in the norm of the larger space, but, sorry, differentiable in time if you look in the norm of the larger space, and but continuous in time if you look in the more restricted space. And this is a space you want, because this space that's going to contain the moments that you need in order to get a very good flow. So that, the proof of the things, it's a very lengthy, I'm not going to say, I'm going to write a few statements, but what it brings to us is the analog to the role of the Sobolev embedding theorem, which is a lower bound for your operator, right? That is somehow, sorry, for the functions in the Banach space independent of the operator, but also it brings the Poincare constant, which is something that starts to depend on the operator itself. And I tell you what it is, and that's why it works wonderful. So, okay, so that's the abstract theorem. So basically, when we have this very extenuated papers of tons and tons of pages, is really behind these three properties. Okay. So how do you get there? One of them is the important objects called that, which is really was generated by a work of Bobby Lev in '97, with the search of answering the question, if you start with, which by now we know how to do it, but when he started, it was a partial result, but very profound, which says the following. If you start with the Boltzmann equation and your initial data, in the case Gaussian is Maxwellian, is it true that that property propagates in L infinite? Arkwright thought it was true, he didn't know how to prove it. Many people tried to prove it, he didn't have a clue. The answer is yes, you can do it, but there is a first step, and this is what Bobby Lev said. If you start with a distribution function, and he called, right, that the temperature is bounded, what does it mean? It's actually going to say that if we start with a distribution function, that when you multiply it by an inverse Gaussian, that remains in L1, right? That property propagates. And if you can prove that, then you can pass to L infinite. So in other words, you can never do anything in the Boltzmann equation unless you start to understand what happened with the space of moments. So the inverse of the Gaussian is to say, right, that the solution of the Boltzmann equation for hard potentials would have all moments not only bounded, global in time, but actually summable, right? Because you have to form a series. I'll go back to that. But that is actually super important also when you do numerics, because you want to decide what is your computational window. And the computational window is going to depend on the initial data. It's not like the heat equation that you have a domain, you compute in that domain for any data. Here, you have to cut off the domain because you're computing a probability density. And you have to decide what is where you're going to cut. And that depends on the initial data, okay? This is a space homogeneous result, Manuel. And I know that there are many nuisances like bumping tail or things like that, that it would be a fly and perfectly done in a problem on a space homogeneous, and it brings a lot of problems for the space homogeneous. It's a lot of things that, you know, subtleties. But here is the first lemma, and has to do how do I get the control of what happens of the positive part of the operator. Because the Boltzmann equation, even written in weak form, right, has a positive contribution if you take polynomials that are all positive. And that's actually the very important object, is that we do these calculations because the Banach space that we are going to be choosing is L1 with a Lebesgue bracket, okay, which is this bracket. That bracket, I remind, some people call it Japanese bracket. I don't like that word. And this is the way you define this object. So x squared to the 2k is actually the 1 plus x squared to the k. All right. So the, or if you wish, is right. Okay. So if I put, say, v like this is by definition is 1 plus v squared to the 1/2. Okay, that has the correct homogeneity. I mean, you think it's going to make things more difficult? Actually, they don't. Okay, it's much natural. It's the space, and the reason is, as you increase in k and you call the spaces L1k to be all these f's such that f multiplied by v to the k or to the 2k, whatever, integrated, be bounded, right? So if k increases, right, then the L1 is included, the L10 is included in L1, in L11 and L1k for k larger than that. So they nest all of them very well. Okay. The other, or no, maybe the other way around in that case. All right. So then we want to make the following statement. I'm not looking at the weight function, which is inside the collision operator. So this is about the weight. And I said the following. I'm going to take these functions which are convex. It could be this one, or it could be this or this one. But this is the one we really need to use. Bobby-Lev did it in this case, but this is the one we extended to all analysis we do for mixtures, polyatomic gases, and so on. And we said the following. I look at the positive contribution of that weight, right? On the, remember here is the G was the G function. I didn't write it here. Yeah, it's here, right? So the G plus is this part, okay, with this. So this term matters. Then look what happened. And this is, for me, was like magic. This is popping a rabbit from a hat. That was the original, where Fourier was in 3 dimensions for hard spheres, and then he used special functions, and we will be able to generate, to extend it, even with Bobby-Lev and Pamferov, to hard potentials, and a lot of work has been done since then. So essentially what you said is that I look at the weight in the post-collisional velocities, and I can actually show, and here is an identity first, an identity, this is exact, that there is a decomposition on which this scattering direction, which is the, remember, is the direction of u prime, you write it in terms of angular coordinates, and then you get that this expression becomes exactly this form. You can pull out a portion of the energy out of here because of the expression we have. I mean, I'll show you some decomposition, and you will understand what that means. And the energy bracket means that is the energy, not necessarily, okay, not necessarily the, so let me tell you what is this. Is to write this form. V squared plus, okay? And it's clear that this is actually 2 plus V squared plus V star squared, which is the same as the conservation of, so this is a conserved constant. It's also a locally conserved quantity. Okay? I mean, because it says it has, you are adding it to the conservation of local energy. I mean, Bobby-Lev does it with the local energy, and here we say this is actually with the local Lebesgue bracket, or the conservation of also the Lebesgue bracket. So essentially what it says is you pull out of these variables in this form a portion of the energy to the k, because here you have a power k. And what is left over with it, okay, what is left over is an integral of a quantity that never passes 1/2. So this never passes 1. B, actually, you renormalize it by the L1 norm, and it's going to get you something here that you pull out the u to the gamma, right? Which is what happens here. It comes from the splitting of the decomposition of the collision kernel times the energy, so the Lebesgue energy to decay. But this lambda that appears here is this integral, and that integral is going to decay in K. It's going to be always smaller than 1, and is actually it decays, so it induces a global stability condition. So it's going to be related to what I like to call the coercive constant, as much as does it the Poincare inequality. And in addition to that, it has a rate if I can put B in LP for P bigger than 1. So if I put L infinite is great, if I put L2 is great, if I put L1, integrability. I mean, remember that the angular part in B in L1 means that it's integrable, so it could be unbounded. The grad cutoff assumes that it is bounded, and that would be in L infinite. And if it is in L infinite, that rate is exactly 1 over K. So it's a super, is that let me put it in other ways. This is telling that if you look at the Boltzmann equation, right, in the weak form, and you take moments, and you take a lot of moments, take it even, because there's even moments, but that's why the 2 to the K, because all of them are going to be bounded in as well, right? Then what happens is this term is going to contract at a faster rate than the negative term. And that is a sign of stability. So the Boltzmann equation in moments is very stable. And it's a way to see it that way, okay? Or the stability comes from the observation of getting the observable. So, and this is, as I said, this is exact, and this is an inequality. But you have to get here. And I stress that because I'm going to show you how it works. Okay, so that is a step 1. Step 2, right? Step 2 is we have to find an equation for moments. Because if I have to prove that the moments are bounded, I really need to see how do we get, some inequality for moments. Well, the moments will not have an identity. Why is that? Because the collision operator, you take the moments and it may have a positive part and a negative part. Precisely, the stability needs the negative parts of the moments. But what is the equation that they satisfy? And the equation that they satisfy is the following. The moments, right? And by now it's the Lebesgue moment. It's really the object that I define here. Okay? If you do this with absolute values, it's hell. This is what people did for 30 years. And this all comes as a breeze, and we can extend it to many problems. This is the same philosophy. So the moment then, okay, satisfies here, up to here, so the moment equation is just to get a bound that takes control of what happened with the comparisons of the potential rate with respect to the Lebesgue bracket, but for the same rate. So that is the inequality. But the rest is actually like a break. But then here comes up something that is obtained, this lambda is obtained from here. Why was that? Because when you actually use this object and you compare it, right, with the weight, so because this is only the weight with a G minus, and put it inside of the weak form, then you're starting to take moments. That's all you are going to be doing. And here you may have an KR expansion, it's binomial expansion, because this has two names, right? One bracket plus another bracket. And then you would expand this binomial, it's a polynomial, right? It's a binomial to a power. You do that expansion and allows you to compute this multilinear form of mixing moments. Okay? It's the multilinear form of mixing moments. But then you have a reminder. And the magic came up that the reminder here has to have a moment of larger order than all of this combined. Okay, and that is what we call the moments estimate. And indeed, this is a very elaborated part of of the theory. And then you can invoke the monotonicity of moments, the conservation of mass and energy and momentum. That is super important. Interpolation formulas for moments, because they have convexity in the way we are writing them with this 2 to the k. We can actually use and then the epsilon Young inequality to actually be able to switch things. I mean, what we want here is to get a superlinear term on the moment. So you have the moment here and here, sorry, and here you have the so the moment, the same moment k, but with a superlinear term, but it comes with a negative factor. This constant is crucial. This is my, between quotes, my Poincare constant. That's the stability constant. And this part, I can completely absorb it. So which was all this positive contribution is completely absorbed by a term that grows in k and says, well, it's exponentially. Yes, it is exponentially, but this is super. That kills everything. It super gets control. You see it in a minute. And then the dynamics are that this equation is actually going to be uniformly held in time, right? For any k that is above some k fixed, I call it the k contractive, which is bigger than 1, and lambda k decays to 0, okay? Well, the lambda k is embedded in a k because I wrote, okay, the ak is here, okay? Oh, I see. I see what I did. Let me just, because I edit this slide. So this is what we call mu k now. It's not lambda k. It's mu k. So the ACK is actually the subject. Oh, the red didn't come up very well. So let me actually take here. So I have the ACK. The ACK is the subject. All right. And I call this a coercive constant. Why is that? Because the way I obtain my short form of the Boltzmann lemma secures that you are going to take K, okay, Kc. Actually, for elastic theory and the classical Boltzmann equation is enough to take it to be 1. For mixtures or other or polyatomic gases, it's you have to take in such a way that you can secure that the that the average or that you get from the L1 estimate of the angular transition is always going to give you here something positive. And that is super important because this comes with a minus sign. And that is the stability condition. And that stays here forever. Because what you can prove then is that this equation, by using comparisons and ODEs, has actually a dynamics that it would give you 2 things. First of all, if you start with k moments, right, you actually get a propagation of that k moment. You always are going to be bounded by the maximum of the initial data or this particular quantity, which takes bk over ck, and this actually goes into the a power that is not going to grow more than 2 to the k. And it says, well, but this is actually growing. It says, but this term is growing exponentially. Yes, that's fine. But for each k fix, it gives me a global moment bound. And then when we actually study tails, what we can do, it allows us to obtain something that is going to get completely under control. And I will stress it later. So, okay, so here is the characterization of BK. Now let me just put it here in another color. And I have the BK here, and the BK shows up here, and okay, and here. And the second statement, one is the generation. It actually, this is extraordinary. sorry, propagation, it generates, basically it says, if you start with 3 moments, instantaneously in time, the Boltzmann collision operator gives you moment equations that would generate all the moments. It's like the heat equation, right? That you start with an initial data, this is direct delta point mass, you enter positive time and bang, it becomes C infinite. And you get this Gaussian shape. Same thing here. It's the same effect, right? So then this is important because as I said, it makes us understand the robustness that you have on the Boltzmann flow. And then you become even self-confident when you do calculations, how you're going to cut off the domain. And if you do hard potentials, you are going to be quite well suited to make decisions based on your initial data, nothing else. The initial data, look, in the generation, in the propagation, the initial data is the moment itself. In the generation, we actually ask something that it has at least 2 moments. It depends on the problem. In other problems, you need to ask at least the moments that corresponds to K, C. You need to ask perhaps more moment, right? But what is interesting is in the generation, what you get is that here you have just the first moment with some power. This is initial data. This is initial data. Here you get the same quotient that you have there, which happens to be the equilibrium associated to an ODE with this right-hand side. And then you have an extra term, which is independent of decay, which has decay in time as it would go for time, for large times, and for short times actually tries to be very, very high there. But you're actually not worried in the sense that you are going to be looking at these objects for the generation properties. No, okay, just a minute. No puedo. So, okay. So then the statement of the problem for the theorem, for the Cauchy problem of the Boltzmann equation is basically you start with an initial data that can be a few moments or a lot of moments. You can always solve the solution in the particular space that comes from the theorem of Bressan that says, okay, I need to have at least, in fact, it's I mean, there is a trick, but let me just make it kind of easy that if I put 2, let me start with 2 plus moments, and that 2 plus moment comes into this space, and then I can actually show that there is this space for which the theorem in Banach spaces, the ODE in Banach spaces is going to hold uniformly in time. And that secures the existence, and that secures the stability for all times. And in particular, you obtain that the solution satisfies the conservation laws. And there is something very remarkable. This proof does not need entropy. If you have the entropy, then the entropy is going to be bounded for all. The entropy is going to be bounded for all times. But for instance, the inelastic theory would not have entropy. So you want to have an existent theorem, and that works for inelastic theory as well. So it's very interesting because all the work of existent theory has always been based on the fact that entropy is needed, or most of it. Or ansatz on that you needed a cutoff in the angular part, or you needed a lot of things. We remove all of that. This way to viewing it removes everything. Then we can actually do the propagation of LP theory. And the question is it that you get the same things? You always search for something. You want a norm, look for an ODE that would be, for now, the LP norm or the LPK norm. Can you do that? Well, it's actually very interesting because in that case, you get an equation of you wonder if you get an equation that it would be like what we got before or a Bernoulli type. And the question is, when you do LP theory, right? Think of L2 with weights. The answer is no, you cannot do. The best you're going to get is this. And now here, Y is going to be, for instance, this form, right? So this is what I would like to call Y. So that would be, let me put it here. This would be Y of t. Okay, so I will get an equation of this form, right? But this form is an ordinary differential equation, and we solve it by majorizing, by putting a majorizing in or the equation for the majorizing is a comparison argument in between ODEs that basically says that this equation only propagates data, cannot generate. So you can generate moments, you can generate exponential tails, but you cannot generate L2 norms. But what it comes up here, that you can only study this L2 norm by doing estimates that are actually going to depend on the L1K norm. So you cannot escape the moments estimate that we did in the first part. You see what I'm saying? Is the only way to go to LP is that you use the LP norms are going to depend on the results that you have on the L1K norms. And the way we've written writing all of this is to say, okay, that means then the moments estimates depend on my coercive constant, which is that red AK, right? That depends on the data, right? But then when I go to the L2 norm, it will degenerate if my coercive constant degenerates. So at the end, it's like Lax-Milgram, okay? So the coerciveness is crucial to understand. Another estimate that is crucial is a lower bound. And the lower bounds actually come from something we've been working a lot in many cases. We started with Ricardo in a paper we wrote for error estimates, but now we extend it to many cases, and with Milana to mixtures and to polyatomic and so on. And basically, this does not depend on the Boltzmann equation. This is only on the Banach space, right? You said, well, I'm taking now L11 is a Banach space, and I actually look at functions that have their mass bounded above and below and their energy bounded above and below. You can take different constants or the same. I mean, that is a little bit technical. For this particular case, it's not that relevant. Moment is 0. They have to be symmetric with respect to the origin, which is okay for the space homogeneous problem. And then you have a little bit more of moments. And if you have that, then you can say, and this is very profound statement, if I look at the convolution of F with the potential rate coming from the cross section, that is going to be bounded by this Lebesgue bracket to the same rate of the potential. And this lower bound is fully characterized explicitly in terms of all this bound. This actually is, in my view, what represses the Sobolev embedding. Has nothing to do with the equation. It's fact on the Banach space, on the L1K spaces of functions that have bounded by a constant. I mean, you fix that constant because that constant comes in this space. So for when we use it, it's great because these constants are the initial mass, the initial energy. And that we have to actually calculate what it is, and we can. Okay. So this, as I said, this doesn't need to have the solution of the Boltzmann problem. That means this lower estimate is stronger than a priori estimate solutions of the homogeneous Boltzmann equation. The lower bound is not necessarily for the case P1 in the L1K spaces, but somehow we noticed with in the work we did with Milana Pavic colleague is that when you do mixtures or polyatomic, you need to have for stability a little bit more is to get this this sharp form of the lemma to get it done. And so we basically have integrated. And then in order to go into the LP theory, I need to do something else which is to go to the Kahneman integral representation, which Kahneman wrote. It was used by Sten Sogge. This uses the strong form of the collision operator. That was another case we use it here. And then we can actually start to do, using this, all of these estimates, and this constant depend on the L1K. And I'm going to skip that. It's very technical, but it's all written, okay? But it's what ties up then the Banach space to the Sobolev space. And then we have we have done some work with Ricardo Alonso and Maya Taskovich, on which we can pass to we can also prove that the derivatives of the solution of the Boltzmann equation are also in Sobolev spaces. And that I needed for error estimate. Okay, I'm going to skip all of these statements of technicalities because they are very technical. I'm just going to say the properties of the exponential moments and summability. And this is very interesting because what we have is what I was saying. I have the moments, right? I have the LP norms I can do. And now I have the tails. I mean, can I actually talk about, my moments, as I said, the estimates grow in K, right? But not in time. So for K fixed, you can actually get them bounded. But then the question is, can I then say that if I start with an initial data that has this characteristic, and I put here the Lebesgue form instead of absolute value, I'm looking at forms which are F multiplied by e to a rate alpha, right? And that alpha rate is, sorry, I again, here I made a misprint. Here should be Z. Okay, and so here is Z and here is Z. Okay, because I changed notation in the way. So I'm doing it with respect to Z. So, so if I start with an initial data for which F multiplied by an exponential form of this kind is, which is, if you look at this expansion of the exponential, right, is nothing else that to ask, right, that this series of moments, right, the moments summable with respect to a rate Z, is it going to be finite if initially is finite? Or like in the case of generation, if I just start with 2 or 3 moments, I need a little bit more than 2 plus, right? And then, you know, can I actually get that my distribution is going to decay, say Gaussian-like? It's a lot, right? I mean, it's just saying, we said you start with 2 moments, instantaneously you generate all the moments. Now I'm saying I start with 2 moments and then I'm going to generate infinitely many moments, right? And I'm going to generate an exponential tail. That looks like really quite intense. And the answer is yes. You can do first the propagation. If you have an exponential tail that is more, perhaps natural to see. So I start with an initial data, and then it's the moment so the exponential moment I want to propagate, MP, then we can prove there exists a constant rate Z. Now I'm calling it C, not alpha, but the definition would be the same. That is going to be the minimum between the one of the initial data, the one less than logarithm of 2, and then look what I have here. I look at this expression, and this AK is the exactly coercive constant that I found in the moment. And I work very much, and that comes from the identity that Bobilev proved for the first time for Hart-Sphere. He didn't know about that. And if you look at the literature of exponential tails until now, everyone says there exists a constant, there exists a constant. Here we found the exact form of the constant. So this is going to be this number, because you assume this should be the smallest, right? Is the number that is going to enter here. This Z that enters here is the rate there. That means that if I lose the coerciveness, then I would lose the exponential tail. Because if A goes to 0, then here I get the 1 and I have F in F1. Okay, so coerciveness really matters here. I should say, and I don't have time to go to that, if we look at the decay rate to equilibrium, the decay rate to equilibrium, which is the analog of the spectral gap or Rayleigh quotient, is also depending on this constant. So you can really get it out from the data from the beginning. And then you know, if you have the rates and you have the initial data and so on, you would really know what is going to be the tail of your distribution. I think it's something that even if you use it, you know, step by time step. And the statement is, you're going to get that the local, the global solution in time is going to be MP plus this object here. So it's going to be the initial data, which is this initial tail, plus just the mass, which can be renormalized to 1, plus 1. This is a very sharp estimate. As I said, it is a little bit more, but it's going to have, the bound is going to be this, the initial bound plus 1. You cannot ask for better estimate than that. There's a little bit of room that you need to allow. It's not an invariant region, but it's almost as good. The rate degenerates with respect to this constant also. And that constant collects a finite number of k's on which the bk, this 2 to the k, became relevant. But you can actually take it to be finite, okay? And that is a detail a detail in the proof. So this is not going to be changing with respect to k, because we are able to fix the k, and that is fixable because we have the control of what we call the mu k, which was part of the representation we have here, which is how much you contract in the proof of the Poffner identity, as we call it, or the angular averaging, the contracting factor. And then also you have the exponential generation of the exponential moment generations, or the generation of the exponential tails, as we said. Again, here the alpha, so set alpha to be z. And then the statement is somehow similar. And oh, I think I need to put a plus, and now I don't remember. I hear I have a plus. Okay, and so now I said, even if I start with 2 moments, even if I start with 2 moments, in the case of polyatomic gases or with mixtures, you would start with as many moments you need for stability. But in the classical case is 2. Then what you have is that there exists a rate, and now the rate is slightly different. There's not like the initial rate, because it was not exponential. Now you have that is the log of 2 comes as a condition. It would be a number between the smaller between this one and this one, right? And this actually may deteriorate it, because the larger you choose the K0, the smaller it gets, but you fix it, and you fix it according to a number of things on which you have okay, so you have a factor, this factor, which is this mu k, is the one that we know, right? And I remind you that mu k actually decays to 0, and if B is in LP, then decays with a rate. And then you use exactly to find what is the K0, for which you can actually make some part. The contracting is like this kind of using the sort of the Young epsilon-Young's inequality type of arguments, kind of thing. So then we, yes.
I have a question in this context, because I'm interested in moments, obviously. So the question is, I look at this also together with Milana.
Yes.
And I mean, only very briefly, so we got carried away actually from other things. But so the question is, if there is an existence for a moment expansion, and this requires the moments mk actually to decay in K with index K. Or alternatively, your sum over K, which is still present there. If you see on your screen, you write this series there, which is an infinite sum, and it contains this M, but it also contains this K faculty in the denominator.
Right. Okay. So
right, and this means that the moment in principle can grow with K, and I don't like this.
Right. Okay.
I would like to have the moments decay with index K.
Right.
Do you understand what I mean?
So it was a twist around going the proof. That you know, we got a bunch of proofs, but maybe you can improve it. All right. That could be that you can you still have room to get better ways perhaps to remove this. Okay. We have not focused on that. At this point, we know that we have it and we know it comes from. But here is the observation, and it's that when we okay, so we have the moments and we have bounds, right? And the way we did the moments estimates for the moments first, I mean, I can go to the earlier slide, but let me tell you this. It has to do with the moments of the game. That 2 to the k comes from the game. And so the moments of the game is this binary sums, right, of moments with shifts. That comes because you are expanding this energy to the k, and it's a binomial form, and multiplying by f and calculating the moments. There we use it for the first estimate, we use it coarse. And we said, okay, we are actually going to do it by taking the k moment, because the loss is super linear. The loss always will have the shift that comes by Jensen's inequalities, sort of, or interpolation, and becomes super linear. But then the other one says, okay, I put the largest and the smallest, M1, MK, and then I grab them up and goes to 2 to the k is precisely the bound that you get for the combinatorial numbers. Now, we have that for k fixed. And then this is how we did it historically.
So I would like to have it in K. So this is
right. No, wait. Maybe I will. That's a good question, but I haven't pushed it into that frame yet, because for the exponential form, I mean, we discussed it at one point with Ricardo, with Milana, and maybe, you know, much more needs to be said. And the more we talk about the things we discover, we can do it better. And that delays actually many times the way the pace at which you want to publish. So.
I appreciate your optimism.
Right, but the fact is this, Manuel, when we do the exponential tails, it's a great question. Then we do the binomial expansion with the combinatorial numbers. We keep it all. We don't do this coarse bound. And then we split, right? And we split and take the few moments on which we are going to fix, and we are going to use the decay of this mu and the tail of the number of moments, in a sense. It's split with respect to the k number, how many moments you took. The tail, so the exponential tail, there we have something that we call the discrete convolution estimate that allow us to control the tail of the exponential sum in k, right? And then I have left the other ones that I have the upper bound, but then the upper bound, I control it by this constant, right? And then this constant is there to stay, but I can actually choose the number of k's in such a way I again end up getting a super linear type of a super linear ODE for the partial sums of the exponential moments. That is the proof. And it's always the same thing, right? At one point you break even and you say, well, with this number of moments, I can, you know, above certain number of moments, which in this case is k0, I can actually get the control of the rest of the estimate. It's technical, but I would have to give another lecture if you want to hear all
You're
the
very
details.
welcome. So please maybe continue.
I will do it, and even if you know, it's a lecture for a few on the group. But we'll do it. Milana can do it.
I appreciate
Milana and we have been navigating this back and forwards for several months, I would say by now.
Please continue.
But the fact is that you get this very very, very robust estimate, and I use it numerically. So I'm eating my time. You have seen the mixtures. Milena, have you talked about the mixtures in Manuel's group? Maybe I can.
This is not only my group, so you can probably go fast here. I mean, this is
right. So for the mixtures, I start. This was idea. This was Milena did very nice. It looks very nicely when you click and pulse up. But what you get here is the classical. So what is the interchange law? If you have mixtures and you have particles with different masses, right? Then something very different happens. That would be the elastic law. But if you have a different mass, right, which in the elastic law you would have here 1 and so the center of mass would be 1/2 and 1/2. Here, actually, you get these numbers and or these values, which are the two-body mass fraction, and that actually does a shift of the center of mass towards the heavier particle. And that is physics, right? And that actually allow us to calculate the exchange of coordinates. And this is why I said in the first slide, I want them to do in center of mass and relative velocity, because all of this becomes very natural when you start to study these interactions. All right, and we know how to deal with this. We even know how to deal with the Fourier transform of this. So it's actually very interesting. And then the interaction law comes up here, and you can fully classify it. And then we do have our final diagram. And we can specify, that's what I say, the interaction law is your starting point. If you don't know what is going to happen with interaction, it's very difficult to do anything. Once you have that, then look what we are going to do. Okay, so I classified, the conservation of the scale mass, you get the conservation of the relative velocity, and the energy has this split. And that is going to be my angular average and Pöffner lemma, the mimetization of Wobilet's work. That allows you to say that the positive contribution on the weight is going to be dominated by the negative ones. Otherwise, you lose coerciveness. So we did all the exercise, and I'm actually showing the slides in the same order. You have to write the weak form. You have it. Here we have an entropy. We have it, but we don't use it for the existence. All right. The functional space, that was the tricky thing. What is the bracket? The Lebesgue bracket. The Lebesgue bracket now has to be this particular form, which in the case of elastic theory was a 1. Now here you have to put this sort of, it's not the two-body, it's the n-body mass fraction. It looks at everything. With that, we could make it work. Without it, we couldn't. Someone might improve it, I don't know, but that's what we got. And then we can do the associated norms, even in LP's cases, and we define the concept of moment exactly as in the elastic case. And then I can have all of this. The lower bound lemma, it holds. It holds, and it's actually complicated, but it's the statement that says if I have the masses controlled above and below by a fixed constant for all of them. Momentum is 0, I'm missing a bracket there. And then here, and I have a little bit more than 2 moments, then I can actually take, this would be the collision this is actually the collision frequency term that appears in all the terms of the mixing for each of the components, okay, is bounded by a constant times the Lebesgue bracket or the order J. And actually that, you put that this is the minimum of all of them, and that Lebesgue, and that constant is explicit, okay? So that is the point 1. Second point, can you get the energy identity and the analog of getting the contractive constant? Otherwise you're doomed, you don't have the coerciveness. The answer is yes. And this is where you do this calculation. This calculation is exactly the calculation we had before. As I said, no? we do a split of the energy. In the elastic case, it's trivial. This is the split of Mobilet in absolute value, the one I showed in the, well, I didn't put that a slide, but you do you take these coordinates in this form, and then we can write exactly the split of the energy. And with that, we can do the angular averaging lemma, which says, take for the bracket that corresponds to one species and the other, because they are mixing, this is for the recombination integral, multiplied by that Bij, you have capital I species, that means you have capital I square collisional integrals, right? Including the particle, and that is going to be bounded by a constant times this object on which this constant goes to 0. That was the mu k before. So slowly we could build all the pieces, okay? And it's very important that you pick up a k star for which this number does not pass the L1 norm, exactly as we show it in the other case. And then we actually were able to do these calculations and come up with these pictures that basically, or this analysis, how many moments do you need? Well, if you're going to do masses that are very, very close to each other, to 1/2, and then you deviate very little, you're doing fine. I mean, with you deviate by 1/10 of half, you can actually take what? Maybe 14. You have to always be in the negative part. But if you deviate 1/5, well, you need almost like 35 moments. And if you're going to do electron ions, you need probably more than 5,000. In fact, I calculate should be more than 1 million. Okay? So it's really very interesting. So it's not arbitrary how many moments you need for stability.
Irene?
This encodes the stability.
Irene?
Yeah. Yes.
The number of moments here, it's really the actual number and not like, I don't know, the degree of the polynomial.
No, it's the number of moments that you need in the initial data.
Ah, I see. Okay, thank you.
Okay? To get stability. This is really very interesting because it means that if you don't, you see, this statement says that there will be some k, all right, for which this will happen. And if you don't have this inequality for each ij pair in the mixture, right, that means you will have an unstable mode and you don't want to kick on that. So if you actually get all of this, you can secure, right, unless you do analysis of what to do in unstable mode. But with this, you actually will get the stability condition. You will get the coerciveness uniformly for the system. Okay. And then you have this, the polynomial moment. This is the way we wrote it using the Bernoulli type equation. Now we know how to do it slightly better in the way I show you in the other slide. And we are working on the second version with Erika de la Canal and Milana to improve that. But then we were able to get also the exponential moments. And here in the first manuscript, we didn't specify what was the rate as much as we are going to do it in the second one. Because now we understand much better, okay? Polyatomic gas model. All right, what is that? Well, the polyatomic gas model, again, this is something that Manuel and Milana have been working, and Milana and her former students, Vladimir and Nicola Spatojevic, it's also working on. Let me just say, I don't have time. I want to do some of the numerics, and but here the new complexity is that the equation for the local energy involves the internal energy, right? And while this conserves center of mass, the way the internal energy affects the equation is that the exchange of coordinates actually are going to be subject to that the relative velocity in center of mass and relative velocity coordinates, okay, although it is conserved, you can actually have partition factors on how much they collect from the local and from the total energy. So you want to know if the local energy is just the total or how much you get from the potential energy and the internal energy. And that is the kinetic energy and the internal energy. And then you enter all these partition functions into the model, right? That basically gives you This is going to be dense, guys. A transition probability, right? A transition probability that is a transition probability, right? That is going to depend on all of these factors. This is what it takes B. And it has the classical V and V star, and the classical angular cross-section, the scattering cross-section. But it has the partition functions with little r and big R, which are how you distribute the energy, the portions of local, of, as I said, kinetic and internal energy, and how many parts of the internal energy within itself is capital R, while the, no, little r, while the big one with respect to kinetic and internal is big R. So all of this come, and this is part of the model, and Milana knows that much better than me. And then we have to actually look into the unknown, and we work on the space homogeneous setting. So it's not. And then we were able to obtain exactly all these steps. And the steps is to get the moments estimate, so we can do the Hölder inequality for Bressan, the subtangent condition coming from the moments of the collision operator, and then the one-sided condition that is actually using the Hölder estimates as well. With that, actually, then we end up having the fact that we can treat this statement. Sorry, here I have to do a blending of slides, right? But we got this, well, okay, this is a transition. This is a property on the entropies, as much as the entropy production between for the polyatomic gases, and what would be the equilibrium for polyatomic gases, where you have a partition function which is characterized, or it comes from the fact that you have the internal energy here and weighted by an exponential form of that, okay? So the functional space, what is the bracket? Here is the bracket. The functional space is different. The polynomial is actually, so this is what we have, the L1 space, we get the polynomial order, and then here we actually defined the polynomial of order K is given by this form. And then we have different alternatives of transition probabilities that we can make it work. And in fact, the issue we had was, what is really the transition probability for polyatomic? Well, nothing was, I mean, we were not sure. Milana says he didn't know. It was not a very well-known object. And then we said, okay, let's look for all these functions for which we can get the estimates, the lower bound and the angular average. And then you have 1, 2, and 3, and that basically make it work. And then once you have that, then you push the machinery again, which is to have the estimates, the lower bound lemma. It worked. This is the analog, as I said, to the log-Sobolev inequality, right? So we have the lower bound lemma fully classified. We have actually the angular averaging lemma in a compact manifold. That is the analog, the analog of what Mobilev did initially. It also works, right? And then we have the calculation here of the coerciveness condition that we need on decay as a function of the degrees of freedom. And this is something that Milana produced lately in response of a comment from Manuel, but actually what we have here is the analog to a phase diagram for global stability of the number of moments for potential rates functions as functions of alpha and n equals to 3 according to this table. All right, so that tells you, I mean, there is certain number of moments you have to have initially in order to secure the condition of stability. And so Then we have the moment recursion formulas, all right? And the moment recursion formulas, I come up with this kind of, okay, disregard that because now we actually know how to do that much better. So I'm going to take this out because up to here, take us back to what I show you, the polyatomic scalar equation. Now I am really doing things for a scalar equation in terms of moments. All is the same. The estimate for this ODE is already addressed in the scalar case of the Boltzmann equation. And all of that actually mimetized. So it's just that you look the structure. It's like saying, it's like when people say, well, I used the diffusion equation and I look for the structure and I generate an accuracy form and from there I get the end of the story. So this theorem applies, okay? And that allows us to also do the exponential tails, and the exponential tails from here is the AK. Here you recognize the form, the structure, the AK, and we know what they're going to do because the technique is the same. It's a scalar equation. I mean, there is more difference between scalar and mixtures to do the things, but with the polyatomic, it was just the way to handle all this data and collisions cross-section in order to put it in this framework. All right, so because Manuel wants to see something of the numerics, I'll do that. I don't know how much, I have 15 minutes, how much I have, or I already ate my time.
I think we have 20 minutes, yeah.
20 minutes, okay, that's good enough. I want to say a few things. The numerics I'm going to show you today, because I have something else of discontinuous Galerkin, on Petro-Galerkin, but it's not as nice as I have it, I want to say, on the spectral method. And I'm going to show you something related to Landau, okay? Yeah, this is very new. I'm doing with Jeff Hack and Anna Stekutovich. This, you saw the slide, emmetizing. Look at the Fourier transform. And I said that the Fourier transform of the collision operator is a weighted convolution in Fourier space. All right. So then, okay, that you saw it. Then let me show you how we make it work. We can even make, numerically, we can actually make it work for the space in homogeneous setting as well by putting a good integrator because you do time splitting. And we have done lots of that. But essentially it's the following. We are going to be using the fast Fourier transform, right? And we are going to do two things. You have to do what you miss when you do these calculations, and even with the Galerkin methods, so far no one knows how to do the full calculation of conservation of energy unless you use Schwartz class functions, which are exponential decay basis functions. And that has its shortcoming. It's a little bit somehow similar to Moment's method. So it could not, there may not be a good scheme or a good choice for problems in which you are computing, a very thick tail. Now I'm working with a physicist on a problem for quasi-linear equations for a tokamak flow, and they have an area which is a plateau. It's a kind of a distribution, and then it flattens completely. So it is very difficult to do a good choice in general. But, basis functions are basic functions, and you would actually choose them as you need. So the whole point here is that there is always an error, and the error makes the conservation suffer as much as the positivity. And here's my claim. The positivity is going to follow naturally after if you do conservation, because what the theory of Boltzmann is, the solution is constructed and to be positive if you use the collision invariance, not the other way around, okay? Not the other way around. The solution is positive because it has the collision invariance, mass, momentum, and energy. So in my view, numerically, this is what you need to present. Now, if you do that, right, you have to, and you do it by a spectral-based method, what we do is we impose the collision invariant on every time step.
Can I ask a question?
Yes, of course.
Oh, it's
right.
Just a quick question. When you say positivity, you mean positivity of the distribution function or positivity of the integral of the distribution function?
No, the positivity of the distribution function.
Interesting.
I have had a lot of discussions with people that do spectral methods in Europe, and they said that the most important thing is the positivity, and the answer is no. And when they do that, they lose in conservation of energy, and conservation of energy is catastrophic, because then you let your PDF to run out, and you are not going to get, you are not going to have a second moment that is reliable for you. I agree. That is super important, in my view. Okay, so then what we did is a stagger algorithm. We use it in many cases, which was, to enforce the conservation, right? And so you can do an Euler scheme to advance the time step of the advection operator, even if you put space, and then you decompose the coefficients on the fast Fourier transform. You call the conservation metrics, and or you form the conservation metric in the Fourier space. If you want, you can also do it in probability space, but you do have to do at one point is a correction on the collision invariance by looking at the quadrature. You form a matrix that contains the quadrature points of the collision invariance, and you solve an L2 minimization problem, which is solved in one step because it's exact. You can do it for the Boltzmann equation. And that is actually very interesting, because what you're going to be doing is the order of the collision operator plus an order of n, nothing else. And then that gives you exactly, you can do the correction here on the conserved, the coefficients for the conserved moment, and then you go back. Then there is, when I explained this, I said, okay, here, when you took the conservation is on the fixed time step, and then when you do the time step, you are going to lose also an error to the time integrator, and that is not accounted by this analysis. But we proved that that error is never bigger than 10 to the minus 3, but we get the conservation. And then with this scheme, we have implemented for Boltzmann, for Landau, and worked very well. And so let me just show you some of the examples, and I want to bring to your attention a couple of them. This was a calculation that we did for a mixture with Chenglong Shang electron ions, and it's a very, very, very simple kind of toy model in physics, but it has an explicit way to get the solution. And so, first of all, the Landau equation, which is that you solve for the grazing collision limit, can be actually written as a weighted convolution in Fourier space, that we know, but the weight, right, can be split as a function of as a function of W and as a function of psi. And that basically allows us to get an algorithm which is n log n, plus the conservation is n. So you have an algorithm which is conservative that is going to be, n times log of n plus 1. I think it probably is the fastest you can get on the shop. We have not been able to, we are working with Michael Aden Malik and Torsten Kessler and Sergei Vasyanov, and I don't see anything, any way to improve it. But you can see here, and this is a calculation of Chenglong, this column would be to run the code and kill the collision operator. So you start with a double Ham distribution, and then you are going to get these unavoidable islands, which happened in the collisionless trap states that appear in collisionless. And this is very short time. And then here you actually enter, so here is 0 collision frequency, and here is 0.1, which is kind of heavy. And you can see that in, what was it? Maybe I don't remember, but it was like 20 mean free times. I think it's in the picture here. Yeah, 20 mean free path, 20 plasma frequency units, right? Then you get that this goes into a very coherent state and approaching the Gaussian. Right? Well, how fast it approaches the Gaussian? Well, we said with Chenglong, now we cannot calculate that. That calculation actually cannot be done because we get negative points, and the decay rate to equilibrium, to evaluate it, uses the log, uses the entropy. Then with Clark Penny, who graduated last year, and I have a number completed now, I forgot to enter it, we did this. I told him, it was a warm-up exercise he did 2 years ago. Okay, said, just look, let's refine, we refine a lot the code of Chenglong, we found things that were, was a room to improve. And I said, why don't we compute, because if I'm conserving, even if I start with a, 4-mode distribution, of course, if I do it very large, or if you start with distribution that have power tails, you don't go even to you don't go to a Gaussian in finite time. You get a very degenerate gap. But we do know that if you start on the linearized equation for the Landau equation, there was a decay rate to be of e to the minus t to the 2/3. Can you actually compute that, right? Can you verify that rate? And in fact, we did, and we did by simple being very careful on the conservation. And we did a lot of testing that has to do how many modes you put on and so on. But essentially what we do is we do not plot, we do not, accumulate in the total calculation of the entropy. I do not add the points that have negativity because I don't know what the log is. So I'm not going to do, for instance, Philbé says, I cut them up and, it says put adding a 0. Maybe he does that, but at one point he says, oh no, I just put a positive value. And that actually is bad because that is going to increase on the entropy. So I said, I'm not computing that. So what happened is, and you can see it on the mesh, two important things. Let me see if it's here. At the beginning, the blue are points of positivity and red are points of negativity, right? So we said, I want to trace where this point going. This is the last time, no, this is the initial data. And if you make it run as it goes to this Gaussian shape, you will see that all this blue is around here and the red is on the tail. Now, you're computing f log f. So if this f, right, has this shape decaying, when you multiply by the log of f, this is decaying faster than a polynomial. And that actually is not contributing at all to an error. That, that was actually super interesting because we were able to recover a calculation of a rigorous study of guano strain on which we were able to show that the probability that the decay rate to equilibrium, we put the slope is 6.63 with 24 modes, right? If you do it with 16, it's a little bit too stingy, okay? And then you may get into 6.2, but this is 2/3. This is e to the minus t to the 2/3. So somehow you get as good as it gets for the decay rate. And in fact, both Strain and Guo were very surprised that actually for them, it's an upper bound. And when I even told Guo, he says, but can you actually get the 2/3? I think I can get the 2/3. So that means there is a lower bound. They don't know how to get it yet. They're working on it, okay? Because it's not that this line is here. It should be certainly below, the statement is below e to the minus 2/3 to a rate. And I claim even we found the associate constant to that rate is this, the slope that corresponds to this line in this. So it's really very interesting. And then we did several simulations. This is the work with Clark Penny. We did different, so we test Coulomb interactions, that's Landau, hard spheres, grazing collision with hard spheres, and with Maxwell molecules on which they said that in that case there are spectral gaps, but they did it for the Boltzmann, not for the gradient collision. And we were able to get almost one, but not quite. We were a little bit disappointed. We increased the number of nodes to 32, was a very extenuated calculation, and we were getting there. But look, for the Landau, you go very fast. It's 0.66, that's 2/3. I mean, it's extraordinary. But for the other ones, it takes off. But you can clearly see that there is a trend that changes with respect to the rate. And so now we are with Strain and Chen-Long-Shang calculating the spectral gap, because it's really becoming very reliable, the scheme. And that we do it actually with a DG scheme, because we are using the linearized equation. And so, all right. And then we did a lot of simulations then on plasmas, on runaway formation for plasmas, double layer potentials, and how things could be changing, and doing calculations that are very, that give something that has thick tails. Physicists call it plateaus now, but this is something we experiment also with Michael Abdelmalek, and a lot of stuff came up. Yeah.
Can you quickly, I missed that. Can you explain again Vlasov linear Landau? So Vlasov, yes, basically the free flight, you mean, and then you do linear Landau?
Oh, okay, all right, that's very good
Vlasov
point.
is the coupling with, so this
yes. In fact, the simulation that we do, right? No. This is a good point. So here we have, for instance, for the system is here, but it would be the same thing for the scalar. You take Vlasov. I mean,
you mean Vlasov? You mean the coupling to electric field? Okay.
Right, and then you have the Poisson or the divergence, yes. Right? Of E is minus the density, right? Electrons. Okay. So then
you linearize Landau.
Okay, the linearization of Landau for calculating the spectral gap is so in this calculation we did with Clark, we didn't linearize. This is a non-linear simulation. Okay, and we wait.
Landau. Yes. Okay.
That's right, full Landau, space homogeneous. Because this analysis comes from the space homogeneous.
So this is, okay. So these pictures are space homogeneous.
These are space homogeneous, right? Yes. But these ones are not.
And then you linearize, but you linearize around what? So you have the
Gaussian, the statistical Gaussian, the Gaussian associated to the initial state, the Gaussian with the moments of the initial state. What happens is hard spheres converges exponentially fast with the spectral gap, and the harder the sphere, the faster the spectral gap is, but it's e to the minus t. But Landau converges e to the minus t to the 2/3. So it takes longer. Okay, but the interesting point, but this simulation that we did with Clark is with the Vlasov, because here we are coupling to the electric field. So you have Vlasov and you have Landau.
Sure.
Right? And then what we do is a stagger. So you collide, you conserve. You collide, right? And the collide, you transform, conserve, or come back, conserve.
But here you linearize both hard spheres and Landau.
You can linearize, but here we did not.
Okay.
We did not. Only the linearization comes in the simulations of a spectral gap that I'm not including in this. Okay. But you can.
Okay.
And then, but then all of this actually allow us to understand and visualize very well what were the effect, what people call a runaway, which is to obtain very thick tails that are due to strong electric fields. And the strong electric field, you can do it by shrinking this, for instance, shrinking the channel or enhancing or increasing the bias. So these are fully plasma simulations, okay, in coupling to Poisson. And here you see the effect that corresponds to these runaways. And well, that was parallelized and so on. And then I want to close with something that I think it's very recent that we are doing with Jeff Hack. and started doing the grazing collision limit. So we computed Boltzmann, and we wanted to see if we could approximate Landau and how would we do that. And so we tested with the classical form of the Landau equation, right, according to Landau. And that was approximated by the Rutherford type potentials, right? And actually we understood, it's a paper of 2014, on which we were able to put even a statement, which is a sort of, if you have a conditional solution of the Boltzmann equation satisfying this property, where you have the collision kernel is really the collision kernel is here, all right? It's this collision kernel, right? Where this B epsilon depends on some parameter delta, which is the singularity that you get in the grazing collision. Then we were able to show that there was the rate of convergence from Boltzmann to Landau is different. The physicists knew that, but we were able to quantify it. Now, here is the example that we did. Take the classical Rutherford sine to the fourth versus what we call it, the epsilon linear behavior, the physicists call it, which is sine to the fifth, more singular. It turns out that more singular is better, it runs faster. But the question is, what is the physical one? Because the physics says it should be Rutherford. And this is the calculation that we did. You know, a posteriori, we use the same code that we know the entropy decay. So somehow it says, well, this is as good as it gets, probably. And I don't know if there is anything more on that would actually be that you could do, I mean, to get any better. But of course, it's more. But then Jeff contacted me about 3 years ago, and he says, I want to do a correction of the Landau equation that actually focus on the true Coulomb interaction, on which even the divide screening parameter, right, which is what they use for cutoff may be velocity dependent, but certainly this cross section that is being used should have a dependence on velocity through the angle. That for me was very new, and I've been actually looking a lot into these issues as well. And in fact, there is a way you have to go back and to recalculate the impact parameter. And it turns out that there is a relationship between the impact parameter with respect to this expression here. Okay, and what is this terms here, right? In fact, they said, well, there is a form that you can take from here, and this expression gives you 2r cosine theta over 2. So somehow the cotangent of theta over 2 multiplied by that gives you that, because you can actually need to write this in terms of the scattering angle. Those is nu is the impact parameter, and here is the scattering angle. And it turned out that you use the classical cross-section, and then the Rutherford cross-section is usually written this form times 1 over u to the fourth. I actually could put the u out there. And this constant comes from all physical numbers. And so where does the device screening enters here? It enters into a cutoff on the impact parameter. And once you enter this cutoff on the impact parameter, then you have a new, you sort of enter into this equation. You write the relation of the temperature times the Boltzmann constant and the mass associated to the thermal speed associated to the motion. You identify this parameter gamma, or you define it that way. That would be a definition. You enter here the divide length. You can actually get even that divide length depending on the velocity, right? And which is what it was suggested here. And then we calculate then the Landau, the grazing collision limit with something that becomes velocity dependent. That changes completely the way you pull out the equation of Landau. And so the Coulomb logarithm is not now a constant that pull out like we did in the previous paper, like the work of the Ghosn and so on. Now, the Coulomb logarithm is a function that depends on U. And that means it has to be inside the integral of Landau, inside the local form, right? And that is what we obtain, right? So when you see this sign of theta, here should be a dependence on U. But what we end up getting is that the modified Landau operator is this one. Jeff is now at Los Alamos and he's working with a lot of people there in plasma. So he is a little bit tidy sometimes about what he's going to do with this. And so we have a lot of interesting things. But what is really interesting is that we were able to do the to see a correction, right? So the red here, yeah, is so here is the velocity cutoff Boltzmann versus the constant cutoff. So the solid lines are the original calculations of Landau that we did with Jeff Hack, and it's when you have that this number is a constant that depends on a scaling, and then you can pull it outside. But if you leave it inside and you calculate it, actually it decays faster. And that is in the, I believe, in the spirit of the calculations of the physicist that I learned many years ago. No, I learned actually recently that Rosenbluth, who was a guy that did a lot of particle physics in the United States, and they calculated the Landau equation using the Metropolis code. The Monte Carlo was raised because of the Landau equation. And it had a lot of problems calculating the Rutherford potential. So they realized they could accelerate the flow by increasing the singularity. The physicists knew that, but they didn't know exactly what they were losing. But you are actually converging to something that is not the Rutherford flow, because we computed the Boltzmann equation. And so in other words, if you compute with Monte Carlo, you never compute Landau, you always compute Boltzmann, because you're always colliding, okay? So the Landau is a limit. Now that we have deterministic solvers, we can distinguish these two things. Because if you put the deterministic solvers, you are actually approximating the model in a better way. You are not colliding particles, right? I remember talking to my friend David Goldstein, and he says, all I do, I collide particles. Fine, but you have a model. And if you have a model, you actually, there's a difference between colliding particles and computing a model, in my view. And the colliding part, the BERT scheme is good for homogeneous flows near, that will not have any tails or near Gaussians. And that we know how to do very well also with any other deterministic solver. So the bottom line is there is lots of things to do and to work. It's just that we have to see how we accommodate. And I wanted just to show that we don't know the decay rate we were calculating. We are using, these calculations were done with 16 nodes. Now we are running 24, and that should actually become much better, but I don't have them ready yet. And so with that, I just want to say we did error estimates with Clark, and we have the control of moments in L2, the discrete moments, and the cutoff, and then we come up to beautiful error estimates. We actually reduce it to very much the kind of things we've been doing with moments estimates. We do the moments, we do the sort of moments differential equations for the discrete form of the or the discrete moments differential equation. We get the stability condition and we get error estimates. On the spectral, it's not a spectral accuracy like many people claim. This is an error estimate. You give me the number of nodes and I can tell you the length, and the length of the cutoff is something that I decide on the initial data, and then we can actually put up the, so you are going to get better estimates by actually increasing the order of regularity, and that depends on the initial regularity that you can afford in your solution. I should say we don't know if Landau preserves this, but these calculations, if you do it for grazing collision for hard spheres, which is not the true Landau, then it works. And this, we used all these estimates that come up here were actually obtained from the analytical results of the Villette and Villani in 2003 or 4 that they wrote about the analysis of Sobolev spaces of the Landau equation for hard potentials. Okay, so with that, let me finish. This is extenuating, and here I'm going to thank the people that I need to thank, some of them in the audience. Okay? Okay.
Thank you.
Any question?
Bravo, bravo. Long
it was a long
afternoon for us, a long morning for you.
Yeah, I appreciate the audience, and really it's great.
It's brave. Yeah, we still have some question if there are any before we let you off the hook. Anybody? Well, Irene, I hear your voice suffering, and you have another class today.
I have another class today. That's right, in an hour and a half from now. I have to, I have to do a little bit of preparing.
In California.
Yeah. Okay.
And thank you so much. Right.
You are very welcome, guys, and I really appreciate your attention. I'll stay in touch with everyone. I think the university will open in August, so Andrea, I hope you come back.
Yeah, we're working.
Yeah, we see.
Let's work on that.
How things develop, yes.
Right, very good, very good. So, okay, guys, I stay in touch with some of you, and it was a great pleasure, Manuel. I really thank you very much.
Yeah, no problem.
For me, it was very humble invitation, and I hope I came up to at least a good portion of your expectations, if not all.
Very nice. So,
okay.
I think I will probably just kill the session entirely. I see all of you, whoever I see. Thank you very much, Irene. Right? Bye-bye to all.
Yeah, thank you very much. Yes, bye-bye.
You too. Bye. Bye-bye, guys. Bye.